Good afternoon everyone. So welcome back to Chandu Biology Classes. So we were discussing about stereochemistry and we have covered some important topics of the stereochemistry also. Identifying chiral centers and identifying number of stereoisomers possible for a given compound by looking at the number of chiral centers present in the given compound. Okay. So for example, let's have a quick discussion first of all by looking some examples of previous discussion. Okay. First of all, tell me how many chiral centers are there in this compound?
One chiral center.
And in this compound? There is no chiral centers in this compound first of all, because see this is not a chiral center. See this is methyl group and this is also methyl group now. So we cannot say this as a chiral center. What I told you, the carbon should contain 4 different groups, then we can say it is chiral carbon. Okay, then if there is a chiral carbon, for that particular compound there will be 2 isomers, stereoisomers possible. So one stereoisomer rotates plane polarized light right side, other one will be left side. That is what optical activity we discussed, right? So optical activity means, once again let me show you the image again so that you will get some clarity. This is what optical activity image I have shown. That white light passes through the nickel prism, gives one single polarized light, we can call it as plane polarized light, which upon passing through the solution either deflect right side or left side. So if it is deflecting clockwise direction, plus direction, we can say dextro-rotatory. If it is anti-clockwise direction, levo-rotatory, I told you. Okay, 2 isomers. For each chiral center there are 2 possible isomers. Okay, if there are n number of chiral center, what I told you, number of stereoisomers possible, there will be 2 power n. So we have, again, for understanding of this 2 power n isomers, we need to understand that RS nomenclature so that we will get what exactly it is. Okay, so what we discussed in the case of RS nomenclature. See, it's an absolute configuration given by based on CIP rules, Gold-Prelog rules. As per this, priority should be given based on their atomic numbers. More atomic number, more priority. So this RS nomenclature can be given in wedge dash notation and Fisher forms. Okay, right. Let us have a quick look into it with 1 or 2 examples, then we will see the PYQs that we are discussing from the last class. Okay, right. So first of all, tell me, here I have Br and hydrogen. Tell me, does this is a chiral center or not? Yes, chiral center. If it is a chiral center, we can prioritize the groups attached now based on their atomic weights. So which is more atomic weight here? Bromine, 1. After this, methyl group here, ethyl group here. So both of them carbon, but here again one more group is connected now. So this will be prioritized, 2. And this is 3 and 4th one. So now number 1 priority, first to priority second we need to move. So from here to here if we move, what direction it is? Clockwise direction. So clockwise direction and least priority group is on dashed line. So it means properly clockwise, least priority and dashed line means what is the configuration? R configuration. And those who are watching online, if you are not knowing like how I am prioritizing these or how I am giving R or S configuration, just watch the previous video on this stereochemistry part. Okay, right. So what is this? R configuration. So similarly, if I take its mirror image, so I can put here hydrogen, here Br. So what happens now, tell me? It becomes like, these are changing now. So you can take here 1, 2, 3, 4 if I write. So this is also clockwise rotation only, but least priority group is on solid line. So configuration becomes opposite. So it becomes S. One is R, another one is S. So these are the 2 stereoisomers. Particularly I can say these are enantiomers. What I am saying? I am using a new word called enantiomers. Enantiomers. So what are these enantiomers? See, enantiomers are stereoisomers which are non-superimposable mirror images. First of all, these are mirror images or not? Yes. So mirror images means like just take your right hand and left hand. These are also mirror images only now. And I am saying if this is my right hand is having R configuration, then left hand will be having S configuration. This will be the phenomenon in the enantiomers. So right hand you take, keep it on left hand, they are not superimposing now. So these are mirror images. If I insert a mirror here, so these are the real images and mirror image. So keep your mirror image, real image and your mirror image, they won't superimpose now. So these two isomers now called as enantiomers. Okay. So now from going from one enantiomer to another enantiomer, what happens to the configuration? See, R becoming S. So in order to move from one enantiomer to another enantiomer, configuration becomes opposite. If it is R, becomes S. If it is S, becomes R. So how to identify enantiomers if 4 compounds are given? Like they will give one compound. Identify its enantiomer from the 4 options. What will be your answer?
If the given one is R, we have to.
Yes. First of all, given one is optically active, and if it is having R configuration, then the emitter that enantiomer should contain S. If our given image is S, it should be R. That's it. Okay. So this is with one chiral center. But if we have multiple chiral centers, for example, given compound contains like 2-3 stereo centers. For example, I am writing carbohydrates, you know now, CH2OH, like OH, H, OH, H, H, OH and OH, H. Like this we are writing. So now how many chiral centers are there here? This one, 2, 3, 4. 4 chiral centers are there. Okay. So now look at this chiral center. Here, as per the whatever the concept we have learned, as per that what we need to prioritize groups, like O group is 1, then next this is CHO, this is carbon. So C oxygen, double oxygens are there, so it will be 2, and the next this will be 3. So what will be the hydrogen is 4. Okay. From 1 to 2 we need to move means anti-clockwise. It means normally S, but least priority is on horizontal line, it becomes R. Okay, R configuration. Is this clear or not? Like that, we need to assign it all chiral center. If I assign it all chiral centers, here it is R. See, carbon number, this is 1, 2, 3, 4, 5, 6. See, your numbering should be like normally IUPAC nomenclature will be giving now. Like first carbon is here, aldehyde is more priorities. Give 1, 2, 3, 4, 5, 6, like this we are giving now. So second carbon is 2R. Okay, and if we give it third carbon, it will be 3S. At fourth carbon, 4R. Fifth carbon, 5R. How I am giving you? I will tell you one trick, simple trick. Wait. See, this is a chiral, like stereochemistry at each of the chiral center. Now, if I want to write its enantiomer, how can I write its enantiomer? Tell me. This 2R should become 2S. 3S should become 3R. This 4R should become 4S. And this should also become 5S. Do you got what I am saying? To go from one enantiomer to another enantiomer, configuration at all chiral center must be changed. If it is R, should become S. If it is S, become R. Like this. Then only we can say enantiomer. Then only we can say they are enantiomers. Is this clear? Now, when the given compound is carbohydrate, like biomolecule, like carbohydrate is given, you need to write most oxidizing group, that is aldehyde group at the top and the CH2OH group at bottom. If the structure is like this, if OH group is right side, give it R. If OH group is left side, give it S. So that's why I have given them directly, like OH right R, OH left S, OH right R, OH right R. This is not chiral center. That's it. Okay, you can remember this trick. Okay, next. Now, if someone asking you how many stereoisomers are possible for this given compound, if they ask, what is your answer? Just count number of chiral centers, 1, 2, 3, 4. So you need to take 2 power n, 2 power 4. It means 16. No? 16 stereoisomers are possible. So how the 16 stereoisomers are counted, sir? See, you can put 2R, like see all R's, otherwise first one R, remaining are S. Like that, how many possibilities are there? 16 possibilities are there. Okay, this is what we need to give. Okay, enantiomers are clear. There is one more term called diastereomer. Before going to diastereomer concept, I just wanted to give, let us solve some questions first. First identify this. Previously we did this question in the last class also. Just I want you to recall all the rules that we have studied. Tell me.
2s and 3s.
Choose the correct absolute configuration for the following compound. See, first one is not a chiral center, remove it. Second one, it is a chiral center, and third one is also chiral center. So now just give it the second chiral center, bromine is 1. After these, two above side also bromine, and see, here also carbon, carbon, bromine, bromine, but here CH3. So second group should be this one, and third one is this one. So 1, 2, 2, 2, 2, 3. So how it is? Clockwise direction. Clockwise direction with least priority is on horizontal. Normally clockwise means R, but least priority is horizontal, becomes opposite. So S. So 2S. And this carbon you tell me? Below carbon? Huh. 1. Next 2. So how it is moving? Clockwise, but least priority? So 3S. So 4S, 2S, 3S. So this is what we got in the last class also. Okay. Now, what is the previous definition I given? Enantiomers are stereoisomers which are not superimposable to each other. Stereoisomers which are mirror images, but they are not superimposable to each other. Then we can call them as enantiomer. So this is one compound. Now if I ask you what is its enantiomer means, what will be the answer? 2S becomes 2R, 3S should become 3R. Then only we can say its mirror image, and this will be considered as enantiomers. Is this clear? Now one more term I am saying, what is that? Diastereomers. So these are also stereoisomers only, which are not mirror images. Which are not mirror images. Which are not mirror images means, if they are not mirror images, then there is no point of discussing about superimposability. If they are not mirror images, then definitely they won't superimpose on each other first of all. See, examples here, CHO, H2OH, and OH, OH. I am writing this compound. Now, so identify, just tell me whether these are mirror images or not. No. Why no? Because above one is same here, but see this is okay, this is mirror image here, first carbon, chiral carbon, but second chiral carbon is not changing now, so these are not mirror images. So these are not mirror images, but the spatial arrangement of atoms are different now at this first chiral center. Okay, so these are not mirror images but stereoisomers, considered as diastereomers. Now one more thing I told you, RS nomenclature, give it the second carbon once at this chiral center and this chiral center. What is the trick I told you? If CHO group above, CH2OH below, if in between that, if OH right side or OH left side, S. So what I can give here? 2S, 3R. Now this will be, both of them are 2R, 3R. So if the stereoisomers configuration becoming opposite at all chiral center, then we are considering them as enantiomers. If configuration is becoming different only at one chiral center or only some chiral center instead of all, then we can call them as diastereomers. So to go from one diastereomer to another diastereomer of a compound, stereochemistry may differ at one chiral centers or some chiral center, but not all chiral center. If it is all, then they are enantiomers. Is this clear or not? Right. Now I will tell you one trick here. Here, how many chiral centers are there? So with this trick, if there are 10 questions from stereochemistry in your exam, Using this trick you can able to solve 5 questions now. Okay, I mean whatever the questions based on this topic. See, at one chiral center, take one chiral center, if odd number of exchanges, what I am saying, odd number of exchanges, exchanges means what, this exchange, like groups are there now, say from here to here, what is the exchange, how many exchange from this chiral center to this chiral center, only here, above one, CHO as it is, this group as it is, this is becoming one exchange, that is one exchange. Exchange means both should change now. Okay, so how many exchange? One exchange. So I can say odd, even. If it is 2 exchanges, even. 3 exchange, again odd. That's why I am saying it as odd exchange, even exchange. So at chiral centers, odd number of exchanges if you found, then you can say it as enantiomer. What is that? Enantiomer. So if it is even exchange, you can say identical. What is that? Okay, so this is at one chiral center if we present. But if we present multiple chiral centers, like 2 are there, 3 are there sometimes. In glucose if you see, 4 chiral centers are there. Fructose there will be 4, again mannose there will be 4, like this if we consider. So now what happens here, if more than one chiral center is there, so you can say odd number of exchanges, like odd exchanges are seen, then we can say these are enantiomers. At each chiral centers there should be odd exchange, then we can say them as enantiomers. If it is even means they become identical. Identical means there is no change, both of them are same only, but they just given it to confuse you. So it means even means you can say identical. Next, in case odd even or even odd, then we can say diastereomers. Okay, is this clear? Now based on this, just look at here. Look at this question. This is 2025, last year paper. Tell me, which one of the following is correct for 2 molecules shown? See, look at this chiral center. This is a chiral center now. First of all, identify chiral centers. After identifying, these 2 chiral centers are same, but there is no difference. There is no exchange. They are being as it is. Okay, but here it is above the plane, below the plane. So if one chiral only if one chiral center is changed, then we can say out of 2 only one chiral center is changed. If all chiral centers configuration is becoming differ, opposite I can say, then it will be enantiomer. But here only one chiral center changed now, what we can call? Diastereomer. So 1 and 2 images are what? They relation, they each other, first of all they are stereoisomers, and then next one. Each of them has 2 stereogenic center. This is also MSQ type question. And then next, they are mirror images of each other. Are the mirror images? No. So remove this option. They are diastereomers. Yes, these are diastereomers. Is this clear or not? Okay, this is one basic question. Next, basic but PYQ last year's. Look at this question. Now tell me, the 2 compounds given below are. Yes. Now whatever the concept I have explained previously, now it will work here. Just check. How many exchanges you are seeing here? See, this one exchange, second exchange, 2 exchanges done. So 2 exchanges at this chiral center. Are you clear what I am saying 2 exchanges means? See, first I am sending hydrogen this side, chlorine this side, 1 exchange, chlorine above side, methyl here. So here 2, it means even exchange is done. Okay, and below you check here, hydrogen remained as it is. So these are exchanged. It means odd exchange. If it is even odd, odd even, diastereomer. That's it. Where do we have? Clear. Okay. So if you want, see, this is the simplest way you can solve without having any waste in energy. Another method, if you want, just give RS nomenclature here and RS nomenclature here also. Okay, RS at both chiral centers you give. If they got same configuration here also, then they are identical. If they got opposite at both chiral center here, if it is RR becoming SS, enantiomers. If it is RR becoming RS, diastereomer. That's it. But I feel first whatever I explained, that method is easy. Just find number of exchanges. Okay, next. Look at this question and answer fast. In the first compound, first example, if you observe, at this chiral center you check. See, let us exchange H and methyl 1 and next this one. So this is even, and at this centers you check, no change. So even and 0 means what we can say? Even. So I can say 1 and 2 are what? Identical. So I am saying this as identical. Just go for the next example. See, OH, 1 exchange, 2. So here even, and below 1 exchange. Odd. Even odd means I can say this is diastereomer. Next this one, OH, 1 exchange, odd exchange. Next this one, 1, no, only 1 exchange here. See, only this 1 exchange. Okay, be conscious while solving this. So odd. So odd means both odd mean enantiomers. So look at the options now. See, first one is they are same molecules, yes, same or identical I can say. Second one is diastereomer, yes. Third one is enantiomer, yes. This is perfectly correct. You can check for other options. They are saying second one is enantiomer. No. Odd even odd means diastereomer. So our first one only perfect answer for this. Clear? Next.
Sir,
Yes.
the first one is identical, sir.
Identical.
So let's say there's odd and 0, then what?
Odd and 0 is even now. 0 is even now. You are saying 0, no exchange you are saying.
Yes, sir.
It means 0 exchanges. So even exchange I can say.
One is odd and other is 0, sir. Sir, the first one.
Okay, so if 0 means if we take
You consider it as like even number like here. Okay, no exchange like you can consider even here. Okay. Again see, there is no exchange at one chiral center, exchanged only at another chiral center. One exchange means it becomes what? In a diastereomer, na? So no need of discussing that. See, again if it is odd exchange I can say enantiomer. It is even exchange. Now even exchange, one even exchange means what I told you? Identical. Here it is identical. Here it is remaining identical only without any exchange. So I can say it's a same molecule, like identical molecule. So consider otherwise, consider 0 as even here. So no worries here, nothing. Any confusions are there still? Ask me. If anything is there, ask me.
అంటే Pలో ఒకవేళ అది odd అయ్యి కింద 0 అయితే ఈ odd even so it's a
Diastereomer. If it is odd even, diastereomer. Even identical. Odd enantiomer. Use this code, that's enough. Look at this question. When they are giving one wedge notation and asking us to identify its Fisher notation. So see, we can write this form into this form, that is okay, but for the best way I can say give RS nomenclature at these two chiral centers. Whatever the RS nomenclature got in this, that should be same in the one of these 4 options. That will be our answer. So identify the correct Fisher projection representation of the following compound is. Only one option they are saying. Compound means, okay, now identify.
One is clockwise.
So first one here. Give it. Give it. OH1, 2. So what is it? Clockwise. Least priority is on wedge. So we can say clockwise means R. Okay. So I am erasing this now. At second chiral center, 1, 2. This is also clockwise and least priority on dash. So R only. So both of them are R comma R. Okay, next same RR will be there in which of these compounds? Identify it. See here OH1, this is 2, 3. So what is this direction? Anti-clockwise, and least priority is on horizontal line. Configuration becomes opposite. Anti-clockwise is S normally, but least priority horizontal becomes S. It is S becomes R now. Okay, R. Next, at this chiral center you tell me. BR is first prioritized, and then next this is 2, 3. So where to where? Anti-clockwise, but least priority H. It becomes R. So both of them are RR. So we can go with option 1. And if you want, we'll verify other options also. Let's go with this option. 1, 2, 3. Clockwise, definitely normally R, but least priority is on horizontal becomes S. So S I am writing. And then next here 1, 2. So it is clockwise, normally R, but least priority horizontal becomes S. You got this? So our first option is perfect answer here. If you want, you can verify for other option. Okay, that's it. So first one is correct here. Next, yes.
The normal one usually, if we take RS configuration with respect to OH,
Huh?
OH is on the left, so we can take that. We should be taking that as S.
See, what I told you, that is in carbohydrates, I specifically mentioned there. I told you one more, most oxidizing group should be on the top. Is it that? So that's it. So that's why I am saying that is for aldehydes, I mean aldoses, ketoses you can consider. Glucose, fructose, those things you can take only. Okay. Like because you are bio students, mostly they will ask you from biomolecules like glucose, fructose, all those things. So I told that trick, that's it. Okay. Next. See, whatever you have learned, I want from that. I know you will definitely answer this. Which one of the following Fisher projections of glyceraldehyde have identical absolute configuration? Absolute means RS configuration. Okay, and tell me now. See, either there are two ways to solve. Either you give RS nomenclature or to all this configuration, all the compounds. If all of them are getting like whatever the species came getting same configuration, they are identical, we can say. Or one more method, what I told you,
Number of
exchanges you find, number of exchanges in the given molecule, that will give you the perfect answer. See, to this from J to K, what is the difference you are seeing? See, position of H is same, but OH, this one exchange and 2 exchange. 2 exchanges only, no? Once again check, H is fixed, 1 exchange, 2 exchange. So from here to here, 2 means even exchange. Even exchange means what I told you? Identical. With one chiral center, even means identical. So from J to L you go.
OH is fixed, sir.
See, 1 exchange I can say, 2 exchange I can say. How many exchanges for J to K? J to L? 2 exchange. So this is also even means identical. And if you want, we will check for this one also. Here to here, from J to M. 1 exchange, 2 exchange, 3 exchanges are there. So 3 exchanges means odd. So J and M becomes enantiomers. So they are asking about identical. So identical are JKL. JKL, third option. Easy only now? Right. Next. Let me give you one more question here. Try to find this. Fine. which one of the following statements is or correct for the following compound? First of all, read the options they have given here. It can have maximum of two stereoisomers. See what they are saying? It can have a maximum of 2 stereoisomers, and it can have a maximum of 4 stereoisomers. It is an achiral compound, and it is a chiral compound. First of all, identify does it have any chiral centers? Where it is? See, is this a chiral center? No, both of them are methyl. Methyl means this is not a chiral center. Okay, but here this carbon, this is methyl group, and this is ethyl group, and this is some other alkyl group, one hydrogen. So one chiral center is there. So one chiral center there means how many stereoisomers are possible?
2 power n.
I told you number of stereoisomers possible is 2 power n. What is the n value here? 1. So it means maximum number possible stereoisomers are 2 power 1 means 2. Okay, it means which option is correct? It can have a maximum of 2 stereoisomers. Perfect. This is incorrect. This is also incorrect. It is a chiral compound. So 1 and 4 are perfect. Okay, I think these questions are more easier than your bio questions, right? There is one more concept called meso. Till now what we have studied, one is enantiomer, one is diastereomer. Now one more word, racemic mixture, and one more is meso. Racemic mixture means I told you yesterday, equimolar mixture of 2 enantiomers, not diastereomers, it is enantiomer. One is R, other should be S. If they have an equal amounts in a mixture, then we can say racemic mixture. The resolution, I mean the separation of these two is called resolution, I told you. Okay. Now racemic mixture, if someone asks you, racemic mixture is optically active or inactive? Inactive, because net rotation will be 0 because of equal amounts of R and S configurations. Okay. Now when I am saying racemic mixture, it is a mixture of 2 different compounds. I mean one is R configuration, S configuration. When I am saying meso compound, within the molecule there will be one R configuration, other will be S. For example, you can take try to give RS nomenclature here. First, to this molecule, it is called as tartaric acid and called as mesotartaric acid. Look at here, 1, and this one is carbon, next oxygen, 2 oxygens are there, but here only 1 oxygen is there. So this should be 2 and this is 3. So anti-clockwise means S generally, but least priority is on horizontal becomes R. S becomes R because of least priority. Okay, so it should be R, 2R I am writing. Next here 1, 2, 3. Clockwise should be R, but least priority horizontal becomes opposite S. 3S. See, both groups, above groups and below groups of same are not same, but above configuration is R, below configuration is S. So if R configuration is rotating plane polarized light right side, S configuration rotates left side. Both of them are R and S within the molecule we have now. So net rotation what happens? 0. So meso compounds will be optically inactive due to internal compensation. What is that internal compensation means? Within the molecule there will be one S configuration and R configuration. Due to the equal and opposite rotations, net rotation will become 0 within the molecule. So it is optically inactive. Racemic mixture is also optically inactive, but that is external compensation. Next, here in simple way, in order to identify meso compounds, you just pass a plane of symmetry. Just pass a plane of symmetry like this. Plane you pass from here, it is having equal, like above plane and like above half and below half is same. So I can say plane of symmetry is present in this. Okay, if plane of symmetry is present, optically inactive. So this is optically inactive. Okay, right. So now identify here. See, for meso compounds, how should be the configuration? At one chiral center R, other chiral center S. Okay, now answer this question now from 2020. Of the following given isomer molecules, 1 and 2 are mesoforms is. These two should be mesoforms. In order to make them mesoforms, how the configuration should be? One should be R, other should be S. So R S isomer of 2, okay, and R S isomer of 1 are meso. Is that clear or not? Identify configuration. Yeah, that's it. You got the concept now? That's it. Next. Look at this. This is, we have a question here. You got enantiomers, diastereomers, meso compounds you got. One more concept is there that comes from very basic first. You know this optical activity now? If I have only plus compound or dextro compound, what it will do? It will rotate plane polarized light right side. If only S means left side. Okay, based on this we have a concept now, or we have a question here. So read this question once. See, they indicated plus. So plus mandelic acid, it means dextromandelic acid has a specific rotation of how much? Plus 160. Specific rotation I am indicating with alpha plus 160, clockwise 160 degrees. Okay. What is the observed specific rotation of mixture of 40% levorotatory and 60% dextrorotatory? Okay. So what will be the observed specific rotation of a mixture of 40% levo and 60% dextro they are saying. See, are they equal amounts first of all? No. If they are equal amount, net rotation will be 0. That is what racemic mixture we are saying. But one enantiomer is more than the other. So we can say this enantiomeric excess. What I am saying? So how can you find this enantiomeric excess quantity? Major minus minor. So how much it is? 60 minus 40, 20. Okay, this is what enantiomeric excess. After getting this enantiomeric excess, see, due to this enantiomeric excess, there will be some rotation now. Okay, so that rotation you can calculate alpha mixture by alpha pure into 100. Alpha mixture means specific rotation of mixture, alpha pure means specific rotation of individual isomer. Okay, enantiomeric excess. How much we got enantiomeric excess? 20. 20 equals to, we need to find specific rotation of mixture. So this denominator, alpha mixture we want. This is how much? Pure 160. 160 given now. See here. For plus, see which one is pure? Alpha mandelic acid has a specific rotation of plus 160 means that is for pure isomer only now. For which isomer? Dextroisomer. Whatever it is, plus given, excess one is given. So 160 into 100. So this will be alpha specific rotation of mixture will become 16 into 2, 32. Which 32? Plus 32. Because this is plus 160 now. So our option is 2. Clear this one also. Next. Let me check whether all the things are covered or not. If everything is covered from the PYQs, we will give some little more extra concept that is required. One more question. Look at here. A mixture of alkene and HBr in a mixture of this alkene and HBr, slight excess, HBr is slight excess, in other does not show optical activity because. So this mixture does not show optical activity. Why? They are asking. Tell me what will be the answer. See, when I am explaining hydrocarbons, I don't know whether you remember or not, I have explained the mechanism. Let's go with this again. See, what is the formula they given? Substrate is 4 carbons, but 1 ene treated with HBr. So you can follow Markovnikov rule addition. It means you need to add H plus ion to the more number of hydrogens containing carbon. Why? Because positive charge here, secondary carbon is more stable than the primary. So first add H plus and gives to this carbon we are adding H plus, and the other carbon will have no positive charge. See, positive charge, carbon with positive charge, we are calling it as carbocation. Carbocation hybridization is how much? You tell me first. sp2. sp2 hybridization, what is the geometry? Trigonal planar. It means trigonal planar means within the plane we have molecule. So now what is the negative part here? H plus Br minus. What is the negative part? Br. So that Br minus is our nucleophile. So that nucleophile has a probability to come from above the plane with equal probability. So that if it comes from above the plane, we will get one isomer. If it is come from below the plane, another isomer. Both of them are now enantiomers. Equimolar mixture of 2 enantiomers are, that's it. If it is racemic mixture optically, so it is optically inactive because the product formed is a racemic mixture. Is this clear or not? Right. So we will get this kind of product with plus minus. Plus minus means racemic mixture indication. Okay, clear now? This is chiral center or not? Chiral center generated means here we have racemic mixture, that is optically inactive. Next. Let me come from again. Next, these are the PYQs. Whatever the concepts involved in the PYQs also explained. Now, little more extra information. Yesterday I told you for cyclohexane there will be conformation like chair conformation, I told you. So along with that chair conformation, we also have some other conformation. So cyclohexane will exist in chair conformation, half chair conformation, boat conformation, twist boat conformation. How many are there? Chair, half chair, boat, twist boat. There are 4 conformations are there. Out of all these, chair conformation is more stable. If you observe this potential energy versus their different conformations, see, chair is at minimum energy. It means it is more stable. Minimum energy, more stable. Okay. After that, see here we have one more lower energy state. This is what? Twist boat. Okay, and slightly above that we have a boat conformation, and least stable is at highest energy, that is half chair. Okay, now look at their energies also. If chair conformation is considered as 0 energy level, with respect to this, twist boat is having how much energy more? 5.5 kilocalorie. If they ask in joules, I given yesterday one relation, 1 calorie 4.2 joules. 1 calorie 4.2 joules, you can remember. 4.182, just take it as 4.2 for calculation purpose. Okay, so twist boat is done. Next, boat form, 6.5. Because yesterday they asked for ethane question. I mean, I have shown you for ethane energy difference they given staggered eclipse. So similar way I am giving for this. So half chair it is 10. So 5.5, 6.5, 10. Okay, and how can you remember this order, which is stability order? I will tell you one code word you can remember. Stability order. You can remember it as city beach. Just for having some mnemonic kind of thing. C means chair. More stable is chair. Next, T means twist boat. Next, boat. half chain. Can remember this. Next. This is done. Okay, clear now up to here. And next, we have seen optical activity, like how can we identify, how we are identifying optical activity?
If you can rotate a plane over
This light, we can say this is optically active. So for identifying that, theoretically we are looking at the chiral center. So along with the chiral center, we need to look for other things also. Along with the, if it is containing chiral center, having plane of symmetry is optically, center of symmetry optically inactive. So along with chiral center, there are some compounds that does not contain chiral center, but they are optically active. So for best example, when it comes to bio, the DNA structures are there now, we can say helical structures. So due to that helicity also, compounds are optically active. So compounds having helical structure also optically active. Okay, remember this one. Okay, so optical activity is for because of chiral carbon. Next one is for helicity, and next one is chiral axis, chiral plane, like this we have. I will tell you. See, X. See, on these double bond carbons, we can put 4 different groups. 4 different groups, A, B, C, D, like this. Okay, tell me what is the hybridization of these carbons here? sp2. sp2 means planar now. If this is a sp2, this is also sp2, and both of them are in plane, same plane right now. So the overall molecule also will be in plane, like this molecule will be in plane. When it is having odd number of double bonds, when I am saying it is having odd number of double bonds. But sometimes there will be alkenes having even number of double bonds. For example, C, like this. So in even number of double bonds containing carbon, what happens is this carbon between 1 and 2 carbons, there will be one pi bond like this. Between these 2 and 3 carbon also there should be one pi bond now, because pi bond here we represented. So these 2 pi bonds are formed in perpendicular to each other, like this. If this bond is like this, other bond will be like this. Now tell me, see, it is like this means these 2 groups are here one, there one, and this is like this means one is above, one is below. How these groups are now? Something like different plane. If these substituents are now in different plane, yes or no? Or the substituents are in different plane or not? Yes. If you want to have more clarity, take 2 books, keep perpendicular to each other. Keep that books perpendicular to each other. Now think that whatever the groups present on that books at the terminal will be how they looks, like perpendicular to each other. Just imagine, try to imagine that. Okay. So if they are perpendicular to each other, so it will be optically active. Like see, 4 different groups I have represented here. So now they will be perpendicularly present in each other, so that they are optically active. So I can say this kind of compounds are optically active whenever we have even number of double bonds, and the groups attached here should follow one condition. On one carbon, both should not be same. This should not be same. There must be like AB type. Here also they can be AB also. Here also they can be AB type also, but not like AA or BB type. They should be different. Then we can say it is optically active. Okay, but with how many carbons? Even number of continuous double bonds. So these are called allene molecules. What is that? ALLENE. Allenes are cumulative dienes. What I am saying? Cumulative means they should be continuous. See, I am saying that this is possible when the double bonds are continuous. So this is optically active or inactive, I am saying. active. Okay, so these two groups are within the plane. Now this becomes, one is above the plane, one is below the plane. Okay, now in case they won't ask till now, in case if they ask RS nomenclature in this kind of compounds, what to do, I will tell you one simple way so that we will get this. So first of all, you just draw a line going from same plane to this different plane. So like this. After drawing this, prioritize the groups based on atomic numbers from this end side, tail side. So tail here only now 1, out of this to 1, this is 2. After giving priorities here, then go to there. Do not go that, sir, Cl is here 1 and Br, Cl are more than this. No, don't go like that. First finish it here and go there. So 1, 2, 3 and this is 4. So how this is? Clockwise or anti-clockwise? Anti-clockwise. And least priority group is on, this side, on dashed line. So anti-clockwise means what? Least priority dashed line, anti-clockwise means S. So configuration of this compound is S. That whatever the rules we studied there, use here. I got you can solve, like whatever the concept involved here, it is clear, right? Next one. Sir, if we have like odd number of double bonds, we are saying it is optically inactive because plane of symmetry is present. So for example, I am writing CD. Now tell me, is it optically active or inactive? Odd number are there now? Inactive. Now when we have odd number of configurations, we will get cis trans isomerism, cis trans, or I can say EZ isomerism. What is that? Cis trans and EZ. When we should use the word cis trans, see, to the carbon atoms, this on different carbons, if same groups are present, like AB this side, this is also AB type. See, AA are on same side now, called as cis. BBB are same side, so cis. If AB, like B and B are opposite, we can say trans. This is clear. When cis trans is given, when both attached groups are same on same side. Groups should be same on same side it should be. Now here attached groups are different. Okay, in that case we cannot give cis trans, we should give EZ. Okay, so for example here I am writing this chlorine, bromine, iodine and fluorine. Tell me, as per atomic number, which is more prioritized? Iodine. You can give this 1, 2 priorities on individual carbon separately. 1 and this is 2 on this carbon. And this side 1, 2. So more priority groups are opposite side now. 1, 1 is how this 1, 1 is oriented? Opposite. So it means that should be called as E isomer. What is that isomer?
E isomer.
If priority groups are of same side, Z isomer. If they are opposite side, E. E. Do not use here cis trans, use EZ. E means entag again, Z means zusammen. Entag again, no need of all those things. Okay, E means opposite, Z means same. Okay, is this clear? Clear now? Any confusions are there still? No. So now these cis trans EZ isomers are there now. These are examples for diastereomers. What I am saying, these are examples for diastereomers. Okay, yeah, this is about the thing. Now tell me one last example I just want to project here. Look at this, is it optically active or inactive, they will ask.
It has kinase centers.
This is becoming blurry all the time. Tell me, what is your answer for that?
It has chiral
Does it has chiral center? Does it has chiral center? See, just now I told you, when we have even number of double bonds, optically active if the attached groups are different, like AB type minimum. It can be ABCD type or ABCDE or any other, but not like AA type or BB types. On same carbon should not be same groups, that's it, with even number of double bonds. Instead of double bonds, we have two rings. So this is also like allenes only. Like this ring will be like this within the plane, and this ring will be like perpendicular. So if it is perpendicular, that groups are also perpendicular to these groups now. Do you got now what I am saying? So that we will get a chiral center in that, or chiral axis will get. Okay. So now give the priorities again here. See, it will be mentioned, one will be mentioned like this is below the plane, this will be, this line will be above. Why? Because this is like vertical, but this will be like this. See, Br is here towards us, chlorine is that side below the plane. Are you able to imagine? Yeah, like this you can say. So now what I told you, draw a line, prioritize from tail side, iodine first, fluorine second, 3, 4. So where to where? S. S means least priority dash line. So S means, anticlockwise means S. Is this clear? Sinister. S means sinister, again you can remember. It means left side. Okay. R means rectus. You can remember that words also. Okay, clear now? All concepts are clear. You just practice few more questions, and even you can practice from IIT JAM chemistry bits also. You will feel more confident. I know you can able to solve those questions also, because I extracted this content from IIT JAM chemistry only. Okay.